Okay, on to the last page of the practice exam. So the first question here is an optimization scenario. So it says, ARM has just released a new low-power embedded processor. Your existing compiler optimizations and backend heuristics were developed for CPUs with more physical registers. How would you adjust your optimizations and backend heuristics to generate better performing code for this new processor? So the idea here is I'm looking for certain things, looking for you to think about what optimizations and sort of back end procedures might have to change if you have less physical registers. So we're talking about register pressure and trying to improve that. So we would want less function inlining, right? And less loop unrolling. We might want more of things like dead code elimination, more register spills potentially, more stuff stored on the stack in general. We would want sort of less aggressive scheduling. So we would want to consider when we're scheduling instructions and selecting instructions how many registers we're using and try to scale back on that. So those are the main things that jump out to me. Dead code elimination, I guess also, value numbering. So more aggressive value numbering, maybe global value numbering to try to reduce the number of things we need to keep in registers in general. Those are the main things that I was looking for here. And our heuristics, we might choose something that's, in terms of heuristics, we might use like a less, greedy and more precise register allocation, more precise reg alloc scheme, right? So we might use graph coloring instead of the LLVM sort of greedy optimization for register allocation, because we might want something that does a better job and produces a more optimal solution for that. And yeah, in general, we'd want to, sort of avoid having, a lot of values that we have to keep around in registers for a long time. So we might avoid things like, reordering instructions that cause something to live a longer time. So really, that's what we're looking for here is the fact that we've got something that doesn't have an out of order core, so we do still want to optimize it, but we want to make sure that we're using less registers than we would have used on this larger, more power hungry processor. So that's the idea there. Moving on to part 8, or question 8. What is the halting problem and why is it important to compiler analysis? So hopefully you remember this one. The halting problem states that is impossible to tell in general, or possible to decide, we'll use the technical terminology, in general, if a program halts. And why is it important? It's important because of the sort of the lemma that comes from that, which is that it's impossible to tell any non-trivial program property because those non-trivial program properties can be turned into the halting problem or turned into something that solves the halting problem if we can solve those. Part B, briefly compare static and dynamic analysis. What are the advantages and disadvantages of each technique? So static, no need to run. Right, that's the main advantage of static analysis is we can see if there's a problem or find something out about our code before we even run it. However, it does have, false positives or false negatives. Those can occur, right? So those are the downsides of static analysis. Dynamic generally means that we will find every bug or we'll find all the bugs that we run into. However, we can still have false negatives in dynamic analysis. So no false positives, generally speaking, because if we see a bug happen, then the bug did happen. but we have to run the code. Otherwise, we could say that, generally dynamic, we have more complete information because we know like memory addresses and things that exist at runtime, whereas statically we might be guessing at some of that. But that's really the idea, keeping in mind that static means, the stuff that we did with Clang, where we're looking at an AST, or we're looking at things before we run the code, and dynamic means that we're actually running that code with some sort of hooks that we've inserted with LLVM. And then finally, why does LLVM run some optimizations more than one time? And this is a pretty quick answer, which is, optimizations may expose more opportunities for optimization. Right, so we might do constant propagation, and then because we did constant propagation, we can see that there's a value numbering opportunity that we have the same value, so we can eliminate one of those values. And therefore, by eliminating one of those values, we have some dead code that we can eliminate. So it's often going to be the case that we can sort of run an optimization and expose other optimization opportunities. The other big example is function inlining or loop unrolling, where we expand the scope of the optimizations that are available, and then we can find more, again, values, constants, things like that, code that we can eliminate, code that we can move around, things like that. So there's always going to be some extra optimizations exposed by doing that. And so that's it for the exam. It'd be nice because my cat's hanging out here, and so if you're studying right now and you pick me up, you can see Mimi, and she's hanging out helping me do this exam and being very quiet, so she's been a good kitty. So I'm gonna give her some scritches, and good luck studying for the exam.